Okay, here we've already been through 1 through 4. So we're going to, I have to go from the beginning. Let's go here. Number 5 says, if the time interval is quite long, then the average velocity of a car over the time interval and the instantaneous velocity at a time in the interval can be expected to be close. That is false. Remember, let's say we have a graph of, it's time versus distance, right? See, it looks like this. If we have, that's probably not the best graph to draw. I'm trying to get something that, if we take an average velocity here, that's an average, but the instantaneous at a time in the interval, see the slope of that line? If I take an instantaneous over here, that slope's quite different. If I take an instantaneous, and this is not written the best, that slope's quite different. So the longer the time interval, the less the possibility that the instantaneous velocity and the average velocity will be close. Okay? All right. Number 2 says the derivative of a quadratic function is linear. Now that's true. And I can just show it by giving myself any quadratic function. Even if I do it like this, if I give myself a general, okay, here's the standard form. Let's take the derivative of this guy. Well, this is going to be 2ax plus b. Well, isn't this the same as mx plus b? So the derivative of a quadratic function definitely is linear. Okay? Number 7 says, if a car travels 80 miles between 2 p.m. and 4 p.m., then its velocity is close to 40 miles per hour at 2 p.m. We have no idea of knowing that. Sure, the average velocity between 2 and 4 p.m. is 40 miles per hour, but the car may not have had constant velocity over the whole period of the journey. So that is going to be false. If he asked you the average velocity, sure. But in this case, no. Okay, by definition, the instantaneous velocity of an object equals the difference quotient. Well, that's false only because the instantaneous velocity is the limit of the difference quotient. Okay, this is what we call the difference quotient. This is the difference quotient. But the instantaneous velocity is the limit and is really the derivative, right? This is how we do derivatives the long way. So number 8 is false. Okay, let's look at, whoops, I had a few pages in there. Let's look at 9. So it says, if f of x is increasing, then f prime of x is increasing. That is false. What I want to do, we have here, is look at another, if I go, shoot, it's not it. I'm looking for, here we go. No, it's not it. I was looking for some math that I pulled up right here that says, all right, here we're testing for increasing or decreasing intervals, right? But it doesn't say that if f of x is increasing, then f is increasing. It says if f of x is greater than 0. If f of x is positive, then f is increasing, okay? So if we go back to the PowerPoint, what I want to say is let's give ourselves a counter example of that. Let's say my f of x is negative x squared. And if I graph that, it looks like this, doesn't it? Well, f prime of x equals negative 2x. So here in the negative x's, my graph is increasing, isn't it? It's increasing. But as I move along this line, Actually, I just graphed those. This derivative line looks like this, negative 2x. So it's a line that runs through here, right? So it's decreasing even though my f of x is increasing. Okay, and you can see that on your graphing calculator if you graph these two things. In this, when x is less than 0, my original graph is increasing, but my derivative is decreasing, so that's false. Okay, number 10. Which of the following is not a way to describe the derivative of a function at a point? Well, the only one, we've never talked about y-intercepts when we talk about derivatives. We've definitely talked about limits of secant lines, limits of the average rate of change, and so on. So C is the one that's not a way to describe a derivative. Okay, it says let f of d be the noise level in decibels of a rock concert, d meters from the concert speaker. So here's our f of d. This is the noise, right? And this is d. D is our input. What does f prime of 60 mean? Well, f prime is the rate of change, isn't it? The derivative is the rate of change. So what it should be saying is it's the rate of change of noise 60 meters from the concert speakers. All right? Because the input here is distance, right? That's 60 meters. And this is the rate of change of the noise. Okay. Let's move on. Here, what we want to do is we want to find the average velocity along this interval. Well, at t equals 1, basically the point looks like this. The points look like this. Okay, 145 and 385. Let's take the slope. 85 minus 45 over 3 minus 1 equals 40 over 2 equals 20. Look at my units, feet per second. Always make them match. Yeah, 20 feet per second. Okay, when he gives you that interval, go to those times on your table. Put a box around my answer. All right, next. Find the equation of the line tangent to the graph of f at this point where f is given by this. Okay, well, in order to write a line, we have to have a slope at that point, right? So the first thing we do is we take the derivative. So f prime of x equals 6x, doesn't it? Now, we want it at this x equals 1. So f of x1 is 6. So that's the slope of the line at that point. Once I have a slope and a point, I can go back to my good old y equals mx plus b. I'm going to use my point here, 1, 2. So 2 equals my slope of 6 times 1 plus b. 2 equals 6 plus b, subtract 6. b equals negative 4. So now I have the b and I have the m. So it's y equals 6x minus 4. Okay? I hope that works. Let's look at number 14. We have to do this with the difference quotient, right? So we're going to do the limit as h goes to 0 of f of x plus h minus f of x all over h. So we have f of x here, so let's find f of x plus h. That equals 3 times x plus h squared minus 1. Now I'm going to FOIL this right here. It's x squared plus 2hx plus h squared minus 1. So it equals 3x squared plus 6, right? 3 times 2, 6hx plus 3h squared minus 1. All right, so let's put it all together. Here, I'm going to plug in f of x plus h plus 6hx plus 3h squared minus 1 minus 3x squared minus 1, there's my f of x, all over h. Remember we said at this point, everything without an h should drop out. So I have 3x squared and I have minus 3x squared. I have negative 1 minus a negative 1, so negative 1 plus 1, those go away. So I'm only left with the limit as h goes to 0 of 6hx plus 3h squared over h. Okay, we're going to factor the h out, and we have 6x plus 3h. H goes away, so now I'm the limit as h goes to 0 of 6x plus 3h. Substitute in, that becomes 0, 6x. So, the formula for the derivative of this function is 6x. Then I'm going to say that's f prime. If you went back and did this the short way, 3x squared minus 1, right? Isn't my derivative 6x? So we got it to work. All right, let's look at this one. Here we have this function where t is measured in the year since 2005. It says find f of 5. All right, f of 5 equals 700 minus 3 times 25, so it equals 625. What are my units? 625 centimeters, and it means in 2010, the sand dune, right? Because that's what they're telling us, the height of this sand dune is 625 centimeters. All right, let's find f prime of 5. So f prime of this, if you come up here, f prime equals 700, it's going to be minus 6t. So f prime of 5 is minus 6 times 5 equals negative 30. What does that mean? This is negative 30 centimeters per year. This is year. This is my rate of change or slope at that point. It's decreasing. So my height is decreasing at 30 centimeters per year in the year 2010. Okay? Now, E is interesting. I was doing some investigation on it and I was having trouble, but what I think he wants you to do is to understand that when you take an inverse, you are basically switching the x and y units, okay? So whereas up here, this was decreasing at 30 centimeters per year, when we do an inverse, we've switched the x and the y, and thus we've switched the units. So he says, what is the inverse of that derivative at 400, negative 1 over 60? He's saying that, right, so this is now what was y originally, which is the height. So when the height of the sand dune is 400, this thing will be eroding at 1 centimeter per 60 years, right? We had centimeters per year. Ooh, this is still centimeters per 60 years, isn't it? 1 centimeter per 60 years. But the input now is the y. The input now is the y, and that's the height of the sand dune. So when the sand dune is 400 centimeters high, it will be eroding at a rate of 1 centimeter in 60 years. That, I think, was the hardest thing on this worksheet. Okay? Let me know if you have questions.